Good afternoon. Welcome to the third session today in the afternoon. So it looks like we will have a session about quantum algorithms and complexity with two talks. So in the first talk, we learn about simple complexity of learning algorithm. It's a talk by Srinivasan Arunachalam and Ronald de Wolf, and Srinivasan will give.
Good afternoon, everyone. Thanks for coming. I'm going to talk about sample complexity of learning algorithms, and this is joint work with my advisor, Ronald de Wolf. So let me begin by talking about just machine learning. So the grand goal in machine learning is to enable AI systems to improve themselves. This is a vague statement, and this is also ambitious. So something practical that we want to settle for is, can we learn something from a given data? Suppose you have a cluster of information, can we make predictions, can we find future patterns, and so on. In recent years, machine learning has received an enormous boost from the success of deep learning. Deep learning is extremely good at image recognition, natural language processing, and even the game Go. And why is there a sudden interest in this field? It's because there's a flood of available data, there's increasing computational power, and the algorithms community, we are coming up with better algorithms for machine learning tasks. So what's in it for us? What can quantum computing do for machine learning? So here, I just want to clarify something. We can also have the data we have is classical, and we feed it to a quantum computer, or the data may also be quantum. And indeed, we do know of tasks for which there's a reduction in time complexity. For example, the k-means clustering problem, the principal component analysis, the perceptron learning, and even the recommendation system paper that we saw presented earlier today. So studying problems on its own is interesting, but what we are interested in this talk is, can we have a framework of learning that has been mathematically rigorously analyzed and which captures some aspects of machine learning? And what I'll be talking about is the PAC model of learning. This is very well studied in computational learning theory, and it is fairly simple to explain. So PAC stands for probably, approximately correct. So before I get to describing the model of computation, there are some basic definitions we need to get ourselves equipped with. So a concept class is a collection of Boolean functions on n bits. And we restrict ourselves to Boolean functions for simplicity. And this collection of Boolean functions could come from low-depth circuits maybe, or maybe functions computed by DNF formulas, and so on. A target concept is some function from the concept class. And a distribution D is a distribution on all n-bit strings. And a labeled example for a target concept C is a tuple x, c of x, where x is drawn according to the distribution D. So PAC model of learning has a very formal, rigorous definition. But before I get to that, let me explain what a PAC learning algorithm looks like. Here, Pacman is my PAC learner. We have a concept class script C that is a collection of Boolean functions that is known to Pacman. He doesn't know the target concept, though. And naturally, what you want him to do is maybe somehow try to find out what the target concept is. And the way the learning process goes is you first pick a x1, sample it according to the distribution, and give Pacman x, c of x. So now he knows something about the target concept, but this is not too much yet. So he says, I want some more examples. He gets another x2, and he sees x2, c of x2, and so on. And we repeat this process until he sees t examples, and at some point he says, yeah, okay, I'm good now, and he outputs a hypothesis H. And something natural that we hope for is maybe with probability 99%, he outputs a hypothesis H, which is close to the target concept. And this 99% is precisely what probably is referring to here. And this approximately correct, I'll get to in a bit. But this 99% and approximately correct is precisely what's captured by PAC, probably approximately correct. So let me give you a formal definition. So Leslie Valiant introduced this model in 1984 in a seminal paper, A Theory of the Learnable. So using IID labeled examples, a learner should output a hypothesis H that is probably approximately correct in the sense that we just saw. So let me first tell you what approximately correct means. So in the standard way, if you have two Boolean functions, you would say H and C are close to one another, and you would define close by saying what is the probability that H and C differ on some x. But here, what I mean by error is the probability that these two, the concept and the hypothesis, differ is measured according to an unknown distribution D. So this X is sampled according to D, and D is an unknown distribution. So we say a Pac-Man is an epsilon delta learner if for every concept in the concept class and for every distribution D on n-bit strings with probability 1 minus delta, he can output a hypothesis that's close to the target concept. Again, so the point is, you fix a concept, which he doesn't know. You fix a distribution, which he again doesn't know. But the point is, with probability 1 minus delta, he should output a hypothesis that is close to the target concept. And this close is measured according to the distribution D. And that is what is approximately correct. And that is precisely the formal definition of how a PAC model looks like. So what is a good notion of complexity measure? Kind of I've alluded to one notion of complexity measure already in my Pac-Man drawing, that is sample complexity. There is a number of labeled examples that the Pac-Man sees. Another natural notion of complexity measure is time complexity, the amount of time steps that he uses, maybe in processing the data and outputting a hypothesis and so on. In this talk, I will restrict myself to just sample complexity. Just analyzing sample complexity has a fair bit of advantages. The first one is there is no need for complexity theoretic assumptions. We're just working with information theoretic quantities. Secondly, you don't need to worry on the format in which the hypothesis is presented from Pac-Man. And the most important point is classical sample complexity has been very well analyzed in machine learning literature. And we know that it is characterized by a combinatorial parameter called the VC dimension. So let me tell you what this combinatorial parameter is. So VC stands for Vapnik and Chervonenkis. And okay, you have a concept class that consists of a set of Boolean functions. Let's just say for each Boolean function, I write this truth table. The size of the truth table is of size 2 to the n. And I stack all the truth tables of all the concepts in a table. So you have a matrix M, which is Boolean, firstly. And secondly, it has size of the concept class across 2 to the n, where the cth row of this table is a truth table of concept C. Now, the VC dimension is the largest set of columns in this matrix, such that if you restrict your attention to these D columns, it contains all possible D-bit strings. It takes a minute for this definition to sink in, so let me give you an example. And just for notational convenience, I will say these D column indices are shattered by the concept class. So let us say we are looking at little n equal to 2, so Boolean functions on 2 bits. And the truth table has size 4. Now let's just say there are 9 concepts, and you have a concept class on 2 bits. Now, if you look at the first and third column, those are the red columns, and if you look at the first 4 concepts, you see 0, 0, 0, 1, 1, 0, 1, 1. And that is precisely what the VC dimension asks you. So the VC dimension is at least 2, because I can give you explicitly 2 columns, such that if you restrict to the rectangle on these 2 columns, you obtain all possible 2-bit strings. And I've constructed this example in such a way that if I add a third column, I couldn't have obtained 3-bit strings. But here is another example. So this example is again on 2 bits. It has 9 concepts. And if you look at the last 3 columns, you should be able to see all possible 3-bit strings. Yeah, I'm not going to wait for you to figure that out, but you see all possible 3-bit strings. So what is nice about this VC dimension? So it's the following. So the fundamental theorem of PAC learning states the following. Suppose you have a concept class with VC dimension D. Then Bloomer et al. Showed in '86 that every epsilon delta Pac-Man needs to use at least D over epsilon examples to learn the concept class. And they proved an upper bound that was worse by log 1 over epsilon factor. And until last year, this factor was not removed. And Steve Haneke showed that for every concept class, there exists a learner who also uses D over epsilon examples to learn the concept class. So in some sense, I mean, what I began my talk with was some form of a learning complexity, number of labeled examples to satisfy some condition. And then I had a combinatorial parameter. It's purely combinatorial. You have a concept class which is known, just compute the VC dimension. And I'm saying this combinatorial parameter characterizes the learning complexity. So for every concept class that I give you, if I just tell you the VC dimension, that characterizes the pack sample complexity. That's why it's kind of beautiful. So let's go to quantum pack learning. So what can quantum computers do for pack learning? So first, what I mean by quantum, in fact, in pack learning. So Schutte and Jackson in '95 looked at this problem, and they defined a natural generalization of a labeled example, and they called it a quantum example. This is essentially a superposition of labeled examples where the amplitudes are given by the distribution. And this is like most natural generalization that we can hope for from the classical pack model. And how a quantum pack learning algorithm looks like is quantum Pac-Man, that guy right there, this guy, he sees different, he continuously keeps seeing quantum examples. It's like a coherently some process is providing us quantum examples, and end of the day, he again needs to satisfy the standard definition that he needs to learn the concept class, concept C. So one way to see why this is a generalization of the classical model is suppose we choose to measure it. So when you measure it, you see a tuple x comma c of x, where x comes from the distribution D. And this is precisely how I defined my classical pack model. And this at least shows that quantum examples are at least as powerful as classical examples. So we hope for something more. So at least they're at least as powerful as classical examples. Can we hope where they're much more powerful? And indeed they are. Quantum examples are indeed more powerful for learning. If you look at the class of linear functions, and if you look at the distribution D, we know that classically you need at least n classical examples to learn the class of linear functions, but quantumly, a constant number of examples suffice, and this is due to the Bernstein-Vazirani algorithm. If you look at the class of DNF formulas, again under the uniform distribution, the best known upper bound classically is quasi-polynomial time, and quantumly, the best known upper bound is polynomial time. So kind of we're done here. My question was, do quantum examples provide an advantage? And I've kind of answered it, and yeah, that should be good for now. But there's a problem. In the pack model, a learner has to succeed for every distribution D. And the examples that I looked at here, they only succeed for the uniform distribution D. So we still haven't answered the question, does quantum help pack learning? So let's look at quantum sample complexity, the complexity measure associated with the quantum pack model. So a quantum upper bound comes directly from the classical upper bound because the quantum examples are at least as powerful as the classical examples. And Steve Haneke did the hard work for us. He proved an upper bound of D over epsilon. So we are good for now. For quantum lower bounds, the previous best known lower bound was by Atici and Serradio. They proved a lower bound of square root D over epsilon. And Zhang, using similar techniques as what they did, he proved a lower bound he improves the first term to D to the 1 minus eta for constant eta. And what we show in our work is a tight lower bound. We show you need D over epsilon quantum examples to learn a concept class. Now I want to highlight this a little bit more. In the previous slide, we saw an example where you get a 1 versus n separation for a distribution D. And kind of when we started this project, we were hoping at least to get a log D improvement even for when you needed to succeed for every distribution. But kind of what we show now is you cannot get any improvement if you need the learner to succeed for every distribution D. So quantum sample complexity is equal to classical sample complexity up to constant factors. And kind of the way we prove this is we have two proof approaches. One is information theoretic. It's fairly simple, but the point is we get nearly tight bounds. And we use another technique. It's called the optimal measurements. And we get tight bounds using this method. But it involves some messy calculations. So the next two slides, I'm going to talk about optimal measurements and convince you that we have a lower bound of D over epsilon. So let me first begin by talking of the state identification problem. You have an ensemble of M states, psi1 to psi m. And each of them are associated with the probability P1 to Pm. In the state identification problem, you're given a state, psi z, from the ensemble, with probability pz, and your goal is to identify z. Fairly straightforward. And what would you do? You get a state, you do a POVM, you get an outcome, you output the outcome. That is kind of what you would do. And what you need to do is maximize over the set of all measurements so that you can see what is the optimal success probability for this ensemble. But that could be complicated because you're maximizing over a lot of measurements. But have no fear. We have something called a pretty good measurement. It's pretty good, actually. What's good about it is the following. Suppose the optimal success probability is called P-opt, then obviously the success probability of the PGM is at most the success probability of the optimal measurement. But what's interesting is the fact that this cannot be too small. This is at least the optimal success probability square. So far, so good. We know a state identification problem, and we know a way to handle it. But what has all this got to do with learning? I mean, I was talking of learning for so long, and suddenly I'm talking of state identification. So in the quantum pack model, what we get is we receive t copies of the quantum example state, and our goal is to learn a concept approximately. Now, clearly you can see that here I'm talking of, I'm talking of C approximately, and here I'm talking of identifying Z. And the remaining part of the slide, I want to say that you can go from learning a concept approximately to identifying something about the concept which is going to be of use to us. Again, remember the goal? The goal is to show that the sample complexity, that is T, is at least the VC dimension divided by epsilon. So let us say the VC dimension of the concept class is D plus 1 for simplicity. And because we're looking at lower bounds, we can fix a distribution of our choice. I'm going to fix a hard distribution, and I'm going to say quantum Pac-Man for this distribution needs a lot of examples. And so I'm going to fix a hard distribution, a distribution that puts almost its entire weight on the first shattered index and almost uniform weight from S1 to SD. And yes, one more idea that we need is the concept of error-correcting codes. We take a constant rate, constant relative distance error-correcting code. So essentially, this is you can view this as a map that takes a k-bit string to a d-bit string, such that if you look at E of x, E of y, and E of z, the constant distance between these two code words is at least a constant. Sorry, the relative distance is at least a constant. So that's good. And now what we're going to do is, it's going to get a little bit more technical, is I'm going to pick a bunch of concepts in my concept class. Pick 2 to the k concepts from my concept class that are defined in this funny way. So I'm going to pick a concept such that on S0 it's 0, and on the remaining, so the point is we had d plus 1 points. On S0, the concept is going to be 0, and on the remaining d points, it's going to be a code word. Now, if you're kind of losing me here, I'm going to explain this a little bit more clearly now. Again, how am I going to pick these concepts? Sorry. So suppose the VC dimension of the concept class was d plus 1. What does that mean? If you look at these d plus 1 columns, and if you look at the rectangle of these d plus 1 columns, you should have obtained all possible d plus 1 bit strings. And let us say this is the truth table of my concept. So S0 to SD are the column indices, and if you look at this rectangle, this entire rectangle, it contains everything from 0 to the d plus 1 all the way up to 1 to the d plus 1. And because I needed that on S0, the concept was 0, I'm going to discard all the black concepts. Sorry, I'm going to pick all the blue concepts. Firstly, and secondly, what I'm going to do is on S1 to SD, I want the concept to be a code word. So the point is, we had this error-correcting code E, and we had 2 to the k code words, that is, for all evaluations of E on k-bit strings, and I'm going to pick 2 to the k concepts or 2 to the d concepts, such that all these concepts on these d points are precisely code words. So what am I doing? I'm doing a lot of funny things. I talk about state identification, then I'm talking of learning, then I'm talking of error correction. What's crucial is the following. By my choice of concepts, by my choice of a distribution, I can actually show that learning the set of concepts approximately with respect to my hard distribution is equivalent to identifying the k-bit string Z. So that's really the crux here. The whole point of this error-correcting code and the choice of my concepts is to say that learning something approximately is equivalent to identifying a k-bit string Z. And now we are in good shape because we know how to handle the state identification problem using the pretty good measurement, maybe. So learning a concept approximately is equivalent to identifying Z. So suppose the sample complexity is T. That means that if there is a good learner who receives T quantum examples, and with the probability Z, identify with probability 1 minus delta, identifies Z. And remember the goal again. The goal is to show that T is at least d over epsilon. And kind of now, because we are in the state identification picture, we can look at the pretty good measurement. So suppose we consider this ensemble of 2 to the k states equipped with the uniform distribution. What we have is that the success probability of the pretty good measurement is at least the squared success probability of the optimal measurement, which we know is at least 1 minus delta because the packed sample complexity is T. So it remains simply upper bound the success probability of the pretty good measurement. And that's sort of the meat of the calculation. But we can show that the success probability of the pretty good measurement is at most this expression here. And in particular, this implies that T is at least d over epsilon. This is the proof sketch. If kind of you miss what's going on was the following. You have the quantum packed learning, and you want a lower bound for that. And you want to have a grip on the lower bound, so you look at something which you kind of understand better. That's the state identification problem. And the translation from quantum packed learning to state identification is by first fixing a hard distribution, then fixing a set of concepts, which I call code word concepts because they come from an error correcting code. And then you use the pretty good measurement, and you get the lower bound. Before I conclude, I'm just going to talk of one more model of learning, which is fairly interesting and more realistic, and that's the agnostic model of learning. So far, in the PAC model of learning, we saw a label. The Pac-Man kept seeing labeled examples of the form x, c of x. And we knew that there exists a target concept C coming from the concept class. But in a realistic machine learning situation, it could very well be that there is no fixed target concept, or there could just be some noise in the amount of information that you're getting. So how do we model this? This has been well studied, and it's called the agnostic model of learning. So you have an unknown distribution D supported on n+1 bit strings that generates examples of the form x, L. So you have a label L associated with every n-bit string x. And suppose you have a concept class script C such that the best concept that predicts this distribution makes an error opt. That is, if you look at the probability that x, L is drawn from the distribution, we see that the probability that C doesn't classify L is equal to opt, or it is the best predictor that we have for the distribution D. In agnostic learning, the goal is the following. You want to output a hypothesis H that makes error at most epsilon plus the best concept from the concept class. You have to see that in my PAC model of learning, this concept class was coming in the starting, where we had a target concept was picked from the concept class, and you wanted to learn the concept. But in agnostic learning, the concept class is where you want a hypothesis to lie. It is sort of more realistic in some sense. And what do we know about sample complexity? So it was shown that the classical sample complexity is theta d over epsilon square. And unlike the PAC model, we didn't know of any quantum lower bounds for this model of learning. And what we showed in our paper is that even if we have this slightly more general model than PAC model, quantum examples do not reduce sample complexity. So even in this slightly more realistic model of learning, quantum examples do not help. And that gets me to the end of my talk. So in conclusion, what we showed is, if you look at the PAC model of learning and the agnostic model of learning, quantum examples are no better than classical examples. And we wanted to go one step further, and we looked at something which also machine learning people care about. That's a model with random classification noise. And even in this model, we show quantum examples are no better than classical examples. So machine learning is pretty young. There's been a recent buzz in this field for the past 4 to 5 years with a lot of papers in the field of quantizing classical machine learning models. But we still don't have many convincing examples where quantum significantly improves classical machine learning. something in lines of what I've been speaking about and more theoretical, is can we look at more optimistic pack-like models? The learner need not succeed for every concept class and for every distribution, because we know of a concept class, a specific distribution for which we know of a 1 versus n separation. But once you enforce this for all D, kind of you lose all this speed up that you could have hoped for. So can you maybe put some restriction and hope that quantum examples actually do help in the quantum pack model? And with that, I thank you for your time.
Thank you for the nice talk. You have time for questions.
Hi, thank you for the talk. I'm curious about what kinds of restrictions on the distributions might be sort of realistic or useful restrictions to make that you think would still perhaps preserve a hope of having quantum complexity.
Yeah, that's a good question. So what we know is for the uniform distribution, you have this 1 versus n separation, and you could hope for a poly n versus exponential n separation for the time complexity. Not really sure whether, I'm not sure what to hope for. I mean, there could be some distributions, but I'm not sure what they could be.
I guess the question maybe is also, are the problems or the sort of killer distributions, are they limited enough that they can be sort of, is there a sensible criteria that would screen them out?
So it's possible, but I don't know. Maybe Ronald, do you have any? Yeah, I mean.
Thank you.
Ronald said it's future work. Yeah.
So in your lower bound, you used these error correcting codes. Can you say a few words about why they were necessary or useful for the lower bound proof?
So the idea is once you have this once you fix this error correcting code, what's nice is if you look at the distance between two concepts when measured according to the distribution D, the point is because these code words, these concepts are picked according to the code words, the distance, so what was close earlier, according to D, should have been identified by using this error correcting code. So I mean, essentially what I'm saying is if you look at the distance between two concepts, when you measure it with respect to the D, because of the error correcting code property, the distance between them is pretty large. And we want a good learner, which implies that he should have identified Z.
Yes,
in these cases, it's not just that you could have all distributions, but also that you don't know in which distribution you are particularly. Could it help if you could still see all distributions, but as soon as the one is fixed, you would kind of give information about the distribution to the learner?
I don't think I got the question exactly.
So, like in these cases, the learner doesn't know anything about the distribution.
I agree.
But maybe like you could have a learner that works for all distributions, but gets information out of the distribution as well. Like can ask how probable it is to get a certain element.
Oh, I see. Not really sure, actually. I have an answer. Maybe Ronald has an answer.
Yeah, okay.
Any other questions? Yes, Matthew.
Sorry, maybe I missed something. So at the beginning you said you had 2 proof techniques.
Right.
So I guess that was one of them. Could you say something about the other technique, maybe?
I can quickly go through it, maybe, actually. I'm not going to spend time, but I'll just quickly. So, I mean, this proof approach is by information theoretic. So, I mean, the way you use the same way of, you use the same distribution, which puts a lot of weight on S0. That's the nasty distribution I've been always looking at. So if you have a good learner, he should have, this hypothesis should be a good way, this concept is viewed as a d+1 bit string, and a good learner should learn the d+1 string with, he should learn at least a constant number of bits of the d+1 bit string. So if you just look at the mutual information between, so I mean, you can view C as a uniform d+1 bit string, and his hypothesis is a d-bit string, and he knows that the first bit is 0, so he doesn't need to worry about that. So if you just look at the mutual information between the A and B, that has to be at least D, because a good learner has to learn a constant number of bits of the target concept. And then by subadditivity, you have that the mutual information of A and B has to be at least, at most, D times the mutual information between A and B1. That is the first bit. And because, if you look at this, because all the weight of the distribution lies on S0, the probability of getting any useful information together is just 4 epsilon over T times D. Because, the useful information is on the last D coordinates, and they have a weight overall of 4 epsilon. So, and if you just put all these three things together, you have a sample complexity of lower bound of T of D over epsilon. And when you look at the quantum case, in the third statement, you can hope for an upper bound of at most just epsilon times D over epsilon. So you get a lower bound of D over epsilon divided by log of D over epsilon.
Okay, any more questions? Good, so then let's thank again.
Thank you.